Hi, so today we're going to discuss Young's double slit experiment, wave interference, interference in thin films, diffraction patterns, the resolution of a single slit and a circular aperture, the diffraction grating, and diffraction of X-rays by crystals. So in the previous two videos of light, we have used the ray approximation model to study reflection and refraction, and it is known as the field of geometric optics. But here we will study wave optics, which discusses the interference and diffraction of light. And these two phenomena of interference and diffraction cannot be explained using the ray approximation model, but they require including the full wave nature of light. Okay. So as we shall see in the following, in order to produce a stable interference pattern between waves, they must maintain a constant phase relationship with one another, and this is known as coherence. So the waves are said to be coherent with each other in this case. Otherwise, if the phase between the waves is not constant with time, then they are said to be incoherent. So we will now discuss Young's double slit experiment. So a common way to produce two coherent light sources is to use a monochromatic source. Monochromatic means it is a light wave of a single wavelength. To eliminate a barrier with two small slits or openings like this one. Okay, so the light that emerges here from the two slits is coherent because it is produced by the same original light beam. Okay, so the two slits serve to separate the original beam into two parts. And as we have discussed using Huygens principle, the waves spread out from the two slits, as you can see here. So the light here passing, it deviates from the straight line path, as you can see here, and this is known as diffraction. So interference of light waves was first demonstrated by Thomas Young, and this is a Thomas experiment, where it shows a schematic diagram where plane waves here arrive at the barrier, and then and this barrier contains two slits, S1 and S2. So the two slits serve as two coherent light sources because the waves emerging from these two slits originate from the same wavefront here, right? And therefore the two sources they maintain a constant phase relationship with each other, and therefore they are coherent. So a pattern of bright and dark parallel bands appear here on the viewing screen. So these bands are called fringes. So when the light from the two slits arrive at a point here on the screen and combine constructively at that point, such as these maximum points here, then a bright fringe is formed like this one. Okay, and when the light combines destructively, it results in a dark fringe. Okay, so note here that interference does not only occur at the screen, but as you can see from the diagram, it occurs everywhere between the slits and the screen. So we will now consider an analysis model for wave interference. So consider the figure here, and as you can see, the viewing screen is located at a distance L from the slits, and the slits are separated by a distance D. And consider the point P here on the screen, and let theta be the angle measured between a line perpendicular to the screen passing through the midpoint between the slits, so this line and this line, which is the line from the midpoint to P. Okay, so this is the angle theta, and let R1 and R2 be the distances that each wave travel from the slit to the screen. Okay, so suppose that the source is monochromatic, consisting of a single wave, then the waves emerging from S1 and S2 will have the same wavelength and amplitude and are in phase, as like this, okay? So the light intensity at P is the result of the superposition of the light coming from the two slits. So as you can see, R1 and R2 are not equal, but a wave traveling from the lower slit here will travel farther than a wave from the upper slit by an amount equal to delta. So delta is the path difference, okay? So if L is much greater than D, then the two paths are approximately parallel, okay? So we will use this simplification model in which the two paths are parallel, like the case here. So as you can see, delta, which is R2 minus R1, is equal to D sine theta. So the value of this delta, the path difference, will determine whether the two waves leaving the slits will arrive at P in phase or out of phase. So if delta is 0 or some integral multiple of the wavelength, m lambda, then the two waves are in phase at P, and then they will interfere constructively. So the condition for bright fringes at P is delta equal to D sine theta is equal to m lambda, where m is equal to 0, plus or minus 1, plus or minus 2, etc. Okay, so m is an integer known as the order number, okay? So the center bright fringe at theta equal to 0, this one here, has the order number of m equal to 0, and so it is called the 0th order maximum. So this is here the 0th order maximum, and the first maximum on either side, where this one or this one, where m is equal to plus or minus 1, is known as the first order maximum, okay? And so forth for the rest of the orders. If the path difference delta is an odd number of lambda over 2, then the two waves arriving at P here are 180 degrees out of phase, and they will interfere destructively. And so the condition for a dark fringe at P is given by this equation. And note here that this Young's double slit experiment provides a method for measuring the wavelength of light. So we will now consider the distribution of the light intensity I, which is the energy per unit area per unit time associated with the interference pattern of a double slit experiment. So suppose going back to this figure here, so as we said, the two slits represent coherent sources of sinusoidal waves, and by coherent we mean they have a constant phase difference, okay? And also, as we said, the two waves have the same angular frequency because they originate from the same source. So at the slits here, the two waves have equal phase, but at P here, their phase difference, which is phi, this one, depends on the path difference, okay? So it depends on delta, which is R2 minus R1 equal to D sine theta. So we know that a path difference of lambda corresponds to a phase difference of 2 pi radians, right? So we have the ratio delta over phi is equal to lambda over 2 pi, so phi is related to delta through this equation, and so phi depends on the angle theta. So this is the angle theta here, right? So the following equation here gives the time averaged light intensity at an angle of theta, and we will not show the derivation here, but it can be found from an analysis of the electric fields arriving at the screen from the two slits. So I max here is the intensity at the point O here, okay? So the figure here shows a plot of the intensity versus D sine theta for the case of L much greater than D. So we will now discuss interference in thin films. So interference can be observed in many situations in which a single source of light splits into two coherent light sources and then recombine. And one of these situations is interference in thin films, such as a film of oil on water or in a soap bubble where colored bands appear as a result of interference on the bubble. So consider a film of uniform thickness T and index of refraction N, and we will use a simplification model in which a light ray that is incident on the film is at an angle that is nearly normal to the film, okay? So as you can see, two rays are reflected from the film, one from the upper surface and one from the lower surface. And so the second ray is reflected after being refracted and traveling through the film. So because the film is thin and its sides are parallel, the reflected rays are parallel, okay? And so rays reflected from the upper surface can interfere with rays reflected from the lower surface. And to find the conditions for constructive and destructive interference, we first note 2 points. So one is that an electromagnetic wave undergoes a 180 degrees phase change upon reflection if N2 is greater than N1, and no phase change occurs if N2 is less than N1, okay? And the second point is that the wavelength lambda n of light in a medium of a refractive index n is given by this equation, which is lambda over n, and lambda is the wavelength of light in free space. So according to this point here, ray 1, which is reflected from the upper surface, undergoes a phase change of 180 degrees relative to the incident wave. And ray 2, because it is reflected from the lower surface, for ray 2 there is no phase change with respect to the incident wave, okay? So ray 1 is 180 degrees out of phase with respect to ray 2, and this is equivalent to a path difference of lambda n over 2. But there is also an additional phase difference between ray 1 and 2 that comes from the extra distance that ray 2 travels, which is approximately equal to 2t. So the total phase difference between ray 1 and 2 is the 180 degrees phase change upon reflection, plus this path difference of approximately 2t. And so, for example, if the path difference 2t is equal to lambda n over 2, then the two rays will recombine in phase, resulting in constructive interference. So the general condition for constructive interference for a thin film is given by this equation. So the term m lambda n comes from the path difference between ray 1 and 2, and the second term of lambda n over 2 is due to the 180 degrees phase change upon reflection. Also, we can write this equation in terms of the wavelength lambda in the first medium, okay? And the condition for destructive interference is given by this equation. So if the path difference 2t is an integral multiple of lambda n, then the two rays are out of phase, resulting in destructive interference. So note that these conditions are taken into account the extra additional 180 degrees phase change between 1 and 2 due to the reflection of 1. And also these conditions are valid when the medium above and below the thin film is the same kind of medium, whether the refractive index of this medium is less than that of the film, such as in this case, or greater than that of the film, okay? Still these conditions apply. Because in either case, the two rays 1 and 2 will be out of phase by 180 degrees due to reflection. Also, these conditions apply if the media above and below the film are different, okay? So if the media are different, these conditions apply, but only in the case if both n of these two media both are less than or both are larger than that of the film, okay? But if these two media above and below are are different, but one has a refractive index less than the film and the other a refractive index greater than the film, then these conditions for constructive and destructive interference are reversed. Because in this case, either both 1 and 2 will undergo a 180 degrees phase change due to reflection, or both will have no phase change upon reflection, and so the net change in the relative phase between 1 and 2 due to reflection will be 0. Also for ray 3 and 4, they also interfere, and the analysis is similar to that of ray 1 and 2. So we will now discuss diffraction. So diffraction occurs when waves pass through a small opening like this one, or for example when waves pass around an obstacle or a sharp edge. So diffraction is the spreading or diverging of light from its initial line of travel. And the emerging rays here, so the emerging rays will have a path difference between them. And so constructive and destructive interference happens to this diffracted light, forming what is known as a diffraction pattern, like this one here. So consider as an example a light source like a laser, okay? Passing through a narrow slit like this one here. So a diffraction pattern will appear at a screen placed here after the slit. So the diffraction pattern consists of light and dark areas with a broad and intense central band known as the central maximum, followed by a series of narrower and less intense bands known as side maxima, and a series of dark bands known as side minima. Okay? So we can say that an interference pattern results from two sources interfering with each other, like this case here. So two sources interfering with each other. And the diffraction pattern results from a wave interfering with itself after passing through a small opening or around an obstacle or a sharp edge, okay? So the figure here also shows light diffracted here from a penny. And you can see the bright and dark rings of the diffraction pattern. And there is a central maxima here, a small central bright spot. And note here how this phenomena cannot be explained by geometric optics, because according to geometric optics, if a penny is placed along the path of the light rays, the screen will show the dark shadow of the penny, right? Without the central bright spot and without the bright and dark rings around it. And this shows how it is essential to fully include the wave nature of light to explain the central bright spot and to explain diffraction, okay? So consider light passing through a narrow slit, as shown here, and we assume for simplicity that the screen is placed far from the slit, okay, so that the rays reaching it are approximately parallel. And experimentally, this situation can be achieved by using a converging lens to focus the parallel rays on a nearby screen. And this model of assuming the rays reaching the screen to be parallel is known as Fraunhofer diffraction pattern, okay? And in the case no lens is used and the screen is close to the slit, then the diffraction pattern is known as Fresnel diffraction pattern, okay? And we will not discuss it here. So as you can see here, this is an image of Fraunhofer diffraction pattern, and as you can see, there is a bright fringe at the center at theta equal to 0, okay, and on each side of it is an alternating dark and bright fringes, okay. So in the previous section of interference, we assumed that a slit acts as a point source of light. Here we will show that the finite width of the slit is the basis for understanding Fraunhofer diffraction pattern, because according to Huygens principle, each portion of the slit can be considered as a source of waves, as you can see here, okay? the waves from different portions of the slit interfere with each other, resulting in bright and dark fringes on the screen that depend on theta. So note here that all of the waves that originate at the slit are in phase, but a phase difference is generated between them as they propagate due to the path difference. Because waves from each portion travel a different distance to reach the same point on the viewing screen, that point is at an angle theta relative to the original beam. So let's consider ray 1 and 3 to reach the same point at the screen. Ray 1 will travel further than ray 3 by an amount equal to a over 2 sine theta, which is the path difference between them. So a is the width of the slit. And in a similar way, the path difference between rays 3 and 5 is also a over 2 sine theta, okay? And remember that we could obtain this path difference because we assumed the rays to be parallel. And this is possible only if the screen is at a distance much greater than the width of the slit, as we have seen in the case of interference, okay? So if this path difference between the waves, so this path difference a over 2 sine theta is equal to 1/2 of a wavelength, which corresponds to a phase difference of 180 degrees, then the two waves will cancel each other out and destructive interference takes place. So using this equation here, you can see that if the path difference is equal to lambda over 2, then phi is equal to 180 degrees and destructive interference results. And so the condition for destructive interference is that the path difference is half a wavelength or any integer of wavelengths plus half a wavelength, okay? And this result we have found before from the analysis done on the two-slit interference pattern, where we have showed that destructive interference occurs if the path difference is equal to m plus half lambda, where m is equal to 0 plus or minus 1, etc. Okay. So here, in this case, for a single slit diffraction pattern, destructive interference occurs if the path difference a over 2 sine theta is equal to plus or minus lambda over 2. And note here that this holds true for any two waves that originate at points separated by half the slit width a over 2, because the phase difference between these 2 points is 180 degrees. And to understand why, let's go back to the equation of constructive interference for two sources here. And you can see that the condition for the first maxima is d sine theta is equal to lambda. So in this case of the diffraction pattern, for a ray at the bottom of the slit and a ray at the top, if we consider them as two sources, the condition for constructive interference is a sine theta is equal to lambda. So this means that the ray from the bottom travels a distance of one wavelength further than a ray at the top. And so a ray from the center travels a distance of lambda over 2 further than a ray at the top, and therefore will have a 180 degrees phase difference, and destructive interference occurs, for example, between 1 and 3 and 3 and 5. Okay, so this is why for any two waves originating at points separated by a over 2, which is half the slit width, the path difference between them is lambda over 2, and so the phase is 180 degrees and they interfere destructively. So this equation can be written this way, and this is the condition for destructive interference. So waves from the upper half of the slit will interfere destructively with waves from the lower half. And if we divide the slit into 4 parts instead of 2, we can, and we use the same reasoning of the path difference being equal to lambda over 2, we get this equation here. And if we divide the slit into 6 parts, we get this equation. And if we divide the slit into 2m parts, we get this equation. And this is the condition for destructive interference, okay? So this equation gives the value of theta where a dark fringe is formed, okay? So where a zero intensity is formed. And the positions of the bright fringes are approximately halfway between the dark fringes, okay? And this tells us nothing about how the intensity of the bright fringes vary along the screen. And this figure here shows how the intensity varies. So the central bright fringe is broad and intense and is followed by less intense bright fringes, okay? So we will now discuss the resolution of a single slit and a circular aperture. So here we will show how the wave nature of light limits resolution, and resolution is the ability of an optical system to distinguish between two closely spaced objects. So to understand this, suppose we have 2 point light sources like this one here that are placed far from a narrow slit. And suppose these two sources are incoherent, which means they don't have a constant phase relationship between them. So if there was no diffraction and we do not include the wave nature of light, then an observer at the position of the screen here will see two distinct bright spots or images from the two rays, right? He will see two distinct objects. But because of diffraction, the light coming from each source here will diffract after passing through the slit, and each source is imaged as a bright central spot followed by dark and bright fringes that are progressively fainter, okay? So an observer at the screen here will see the sum of two diffraction patterns, one from each source, okay? So if the two sources are far enough from each other, such that their central maxima do not overlap, like in the case here, then the two images can be distinguished from each other and they are said to be resolved. But if the two sources are close to each other, then the two central maxima will overlap, like in the case here, and the two sources or images are not resolved, which means they cannot be distinguished from each other, okay? So a criterion for resolution known as Rayleigh's criterion determines whether or not the two sources are resolved, and it states that when the central maximum of one image falls on the first minimum of another image, so this is the central maximum of one image falling on the first minimum of the other image, then the images are said to be just resolved. So this is the limiting condition of resolution and is known as Rayleigh's criterion. So you see that the wave nature of light and the resulting diffraction puts a limit on the resolution of images. So the figure here shows diffraction patterns from circular apertures. First, when the objects are not too close, they are resolved. Then when they are just resolved here, when their angular separation satisfy Rayleigh's criterion, and then when they are not resolved here, okay? So using Rayleigh's criterion, we can find the angular separation, theta minimum, subtended by the sources at the slit for the two sources to be just resolved. So in the previous section, we have found that the first minimum for a single slit diffraction pattern is at the angle that satisfies sine theta is equal to lambda over a, where a is the width of the slit. And according to Rayleigh's criterion, this angle is the smallest angle separation for which the two sources are resolved, because it corresponds to the situation when the central maximum of one image falls on the first minimum of another image, okay? Because lambda is much less than the width of the slit A in most situations, we can use the small angle approximation and sine theta is almost equal to theta, and we write this condition, which is the limiting angle of resolution for a slit of width A, and it is measured in radians. Okay, so this is Rayleigh's criterion for a single slit. And so the angle subtended by the two sources at the slit must be greater than lambda over A for the two sources to be resolved, okay? And many optical systems use circular apertures rather than slits, and for a circular aperture, an analysis shows that the angle of resolution is given by this equation, okay? Where D is the diameter of the aperture. So an example is the astronomical telescope, which uses a circular aperture at the end of the tube, and when light passes through that aperture, it diffracts, which affects the ability of the telescope to resolve light coming from two closely spaced stars. And so the resolution is limited by the wavelength and the aperture size. So this is why an optical microscope cannot distinguish details shorter than about half the wavelength of the shortest visible light wavelength. But for example, in an electron microscope, as we will see in another video, the electrons have wavelengths 100 times shorter than that of visible light. So the electron microscope can distinguish details 100 times smaller than that of an optical microscope. So to understand the resolution limit further, let us consider a circular aperture which is used in many optical systems, okay? So as we have seen, the angle of resolution for a circular aperture is given by this equation, where D is the diameter of the aperture and N is the refractive index of the medium, okay? So the smaller the angle is, the higher the power of resolution. So consider this figure here for a circular aperture. As you can see, the two objects are separated by a distance x, and suppose that the distance from the objects to the aperture is L. Then according to Rayleigh's criterion, the resolution limit, which is the minimum angular separation between the two objects for them to be resolved, is given by this equation, okay? So for a small angle, the arc length here, S, is approximately equal to the distance between the objects x. And we have x is equal to L theta, okay? And so the resolving power is given by this equation, okay? So the less x is, the higher the resolution, which means finer details can be seen. And another way to look at it is through the concept of numerical aperture, NA, which is used for a lens, for example, in a microscope. So the numerical aperture for a lens is a dimensionless number that defines how much light can enter or exit a lens. So the lens collects light in the form of a light cone, as you can see here. The numerical aperture, NA, is equal to n sine alpha. N is the index of refraction of the medium in which the lens is working, and alpha is the half angle of the cone of light. So alpha must be greater than the angle at which the first diffraction order appears, which is this angle, for the lens to be able to resolve an image, okay? So sine alpha is equal to D over 2 over F. And we substitute this here, because in this case L is equal to F, and we get this expression, okay? And so the numerical aperture of a lens is related to the resolving power of that lens, okay? And so we can increase resolution, which means we can decrease the minimum separation between two objects x for them to be resolved by decreasing the wavelength. Also, we can increase the refractive index, such as a lens immersed in oil. Also, we can change alpha to increase resolution. So a lens with a large NA will be able to resolve finer details because it will be able to collect more light. so the cone of light will be larger, okay? So let's consider a microscope. The objective lens in a microscope shown here is the optical element that is closest to the specimen, okay? So the objective lens gathers light from the specimen, and the figure here shows objectives with different focal lengths. So the refractive index n in the equation is of the medium between the cover glass and the front lens, okay, of the objective. And this medium can be air, water, or oil. So as you can see, objectives with a shorter focal length have a wider angular aperture and therefore have a higher numerical aperture and resolution. So we will now discuss the diffraction grating. So the diffraction grating consists of a large number of parallel slits that are equally spaced. So the figure here shows a cross-section of a diffraction grating. A plane wave is incident normal to the plane of the grating, okay? And then light waves diffract at each slit. And those diffracted beams, they interfere with each other, forming the final pattern observed at the screen here. So for a certain point at the screen at an angle theta to the horizontal, as you can see here, different waves would travel different path lengths before reaching that point. So the slit separation is d, and the path difference between the waves from two adjacent slits is equal to d sine theta. And let's assume that the distance between the grating and the screen, L, is much larger than d, okay? So if this path difference is equal to one wavelength or an integral number of a wavelength, then the waves from all slits will be in phase at the screen, resulting in a bright line. So the condition for maxima in the interference pattern at an angle theta, if the light is normally incident to the plane of the grating is given by this equation, okay? And as you can see, this is identical to the condition for a bright fringe in the interference of Young's double slit experiment. So this equation of the diffraction grating is valid for any number of slits from 2 to any number n. So because this is the same equation used for a two-slit interference pattern, the locations of the maxima are the same for any number of slits, but the intensity distribution, as we will see here, will change with the number of slits, right? So the intensity is sharper the more number of slits. Also, this equation can be used to calculate the wavelength lambda by knowing the grating spacing d and the angle of deviation theta. And the figure here shows the intensity distribution for a diffraction grating. And as you can see, the maxima are sharper than the two-slit interference pattern, and the dark areas are broader in range. Also, we have the figure here, which shows a diffraction grating spectrometer. So the light to be analyzed, as you can see, passes through a slit, and then a parallel beam of light exits the collimator here in a direction perpendicular to the grating. So the diffracted light interfere constructively at the angles that satisfy this equation. And the telescope is used to view the diffraction pattern, okay? And by measuring the precise angles at which the maxima appear for the various diffraction orders, the wavelength of the light can be determined. And note here that the spectrometer is a useful tool in atomic spectroscopy, where light from an atom is analyzed to find its wavelength components. So these wavelength components can be used to identify the atom. So it is like the blueprint of the atom, okay? So we will now discuss diffraction of X-rays by crystals. So we have seen in the previous slide that the wavelength of any electromagnetic wave can be determined if we use a grating of the right spacing d, right? So X-rays are electromagnetic waves with very short wavelengths of about 0.1 nanometer, which is 1 angstrom. So in 1913, Max Lau suggested that regular arrays of atoms in a crystal, which has a spacing d of about 1 angstrom, can be used as a three-dimensional diffraction grating for X-rays, okay? And this was confirmed by experiment, and it is used to reveal crystal inner structures, okay? So the diffraction pattern is more complicated than the pattern of N slits that we discussed before, and this is due to the three-dimensional nature of the crystal. So for example, here, this pattern is of a single crystal of the mineral beryl, okay? So this is a schematic diagram of an arrangement used for X-ray diffraction from a crystal. So a collimated beam of X-rays with a continuous range of wavelengths is incident on the crystal here, and the diffracted beams from the crystal, they constructively interfere in certain directions, okay, and can be detected by a photographic film. So the photographic film shows an array of spots known as Lau pattern, and the crystalline structure can be found by analyzing the positions and the intensities of the spots in the pattern, okay? So suppose we have the crystal of sodium chloride here, where the red spheres are the Na plus ions and the blue spheres are the Cl minus ions, okay? So each unit cell contains 4 Na plus and 4 Cl minus ions. I'd note here that a unit cell is the smallest geometric shape that can build the entire lattice of the crystal by repeating it in 3 dimensions, okay? And we will discuss it in more details in other videos. So the unit cell for the sodium chloride crystal is a cube of edge length A equal to 0.564 nanometers. So the ions in the crystal, as you can see, form planes. And now suppose that an X-ray beam is incident on the crystal, making an angle theta with one of the planes. Then the beam is reflected from both the upper and the lower plane, okay? So as you can see, the beam reflected from the lower surface travels further than the one reflected from the upper surface, right? And the path difference between the two beams is equal to 2d sine theta, where d is the distance between the planes. So these two beams, they interfere constructively when the path difference 2d sine theta is equal to some integral multiple of the wavelength lambda. This is true for the reflection from the entire family of parallel planes, okay? And so the condition for constructive interference is given by this equation and is known as Bragg's law. And it can be used to find the spacing d between the atomic planes if the wavelength and the diffraction angle theta are known. So thank you for watching. I included some solved examples in the following. Please don't forget to like and subscribe, and see you in the next video.